This presentation has been prepared for the biannual conference of the European Philosophy of Science Association, and it is based on the articles listed here. Here you find also a link to the presentation in PDF. The topic is the classic problem of understanding scientific progress, or the goals of science, and the demarcation problem, or theory selection. Most of this talk will be devoted to define properly why some theories are better than others, the so-called theory selection problem. At the end, I will review how solving this problem can be used, not surprisingly, to define also progress and a meaningful demarcation. So why are some theories better than others? Before looking at the difficult cases of theory selection, those where even the scientists themselves are not sure of what to choose, we should make sure that our philosophy of science gets the obvious things right first. So let us start from a very blatant example of bad science. Any theory of science should rule it out as a bare minimum. However, what is interesting of the example that I am presenting is that, however crazy, it is subtle enough that no available philosophical criterion is able to rule it out. This is also interesting for another reason, because it exhibits a general pattern of pseudoscientific theories, and it also makes apparent why present criteria fail and how we can fix them. So, Forbetto's theory goes as follows. It coincides with Einstein's gravity, except that it assumes that the constant g of Einstein's gravity is actually not a constant, it's changing in time, g of t. We don't need to specify the details of g of t. It is enough to say that the dependence on t will stay almost undetectable until the 1st of January 2022, but it will have disastrous effect after that. It also makes other assumptions that are somehow inspired to G, but not deducible from it. And with these, Forbetto was able to predict correctly the outcome of a national lottery on the 1st of August 2019. An amazing prediction. Yes, he was probably very lucky, but our philosophy of science must be able to deal with lucky pseudoscientists, because pseudoscientists are many, and some of them will be lucky. Science is robust against lucky pseudoscientists. Now, Forbetto claims that we should prepare for the events of 2022, and he asks for 1 billion of research funds to explore the effects of GDT. If we take seriously the claim that in science what matters is only logical coherence, empirical accuracy, falsifiability maybe, predictivity, as many scientists insist, then we should take Forbetto's theory as seriously as our best theories. Why wouldn't we? So, good reason why we wouldn't take Forbetto's theory seriously was expressed nicely by Einstein as following. The grand aim of all science is to cover the greatest number of empirical facts by logical deduction from the smallest number of hypotheses. Now, this is capture, I believe, the point, but there is a big problem with Einstein's answer. How do we count the number of hypotheses? In fact, Forbetto could always introduce a new symbol, call it xi, to express all his hypotheses as xi equals 0. Now, before proceeding, let me pause for a second, because Forbetto's theory is actually giving a typical pattern of many pseudoscientific theories. For instance, they typically accept all standard theories, except for very few new assumptions, such that they describe well a few facts that other theories cannot, and they may even get a prediction right with some luck. They predict no other phenomena in conflict with the observation, maybe with some additional ad hoc assumptions, and they predict new phenomena in the future that are too important to wait for other checks. Importantly, they don't claim to be better than standard theories, they just claim to deserve equal respect. And they avoid any discussion about the simplicity of the assumption because everyone, especially scientists, say that simplicity is subjective and only empirical accuracy and logical coherence matter. Because nobody challenges pseudoscience on point 3, they don't even need to introduce a Xi formulation. But point 3 is the key, because 1 and 2 can always be achieved. Now, let's go back to our formulation of Forbetto's theory, Xi equals 0. This formulation undermines Einstein's definition of the goals of science. I must stress, however, this is not only a problem for Einstein, it is a problem for any view of science. If you tell me, in fact, that you can interpret Xi, and I have no reason to doubt it, and that the law Xi equals 0 is accurate, how can this theory be less than optimal by any standard? This is not a problem for Einstein only, it's a problem for any view of science, anyone in this conference. The unification view of explanation must define what are few laws, few patterns. Falsification it must define and penalize ad hoc hypotheses, otherwise it's useless. Bayesianism must define prior probabilities, or otherwise I can get any answer. Truth likeness must define bold theories, otherwise a list of exceptions will always be the best according to truth likeness. The few parameters goal, often adopted by many scientists, must define how do I count the parameters. Ontological simplicity, parsimony must define how to count basic entities. And also the no alternative argument must define constraints, otherwise I do have infinite alternatives. Tell me any view of progress, of the goals of science, of explanation, of demarcation, or any non-empirical cognitive value, and I can use the same argument, exactly the same argument, to show that it's totally useless. We really must tell clearly what's wrong with the formulation Xi equals 0. We cannot go farther without that. The problem is that the philosophers often hope that scientists might have a domain-specific fix to avoid a Xi formulation. However, the scientists don't bother to answer properly. They may say simply that Xi is not useful. But this clearly reveals the fact that they do not appreciate the philosophical problem, the philosophical need of actually excluding Xi. Saying that's not useful is not enough. As a scientist, I once decided to finally do my job and understand why this formulation is not an option for the theory I know best, the standard model of particle physics. But that led me to identify what is actually a general problem and its general solution, which is expected given that it is a very general trick. So the key issue is in fact that we cannot express the laws of whatever theories as Xi equals 0, where I here is an index of the number of parameters that I may want to have, and at the same time report measurements as Xi equal a central value plus or minus an interval delta. Why? Well, the simple reason why we cannot is that if I measure the quantity Q, which is what I can actually do, and a quoted central value as a connected interval of confidence, and then I translate the result into the Xi variable, this will in general not be connected. Will be a union of disconnected interval. Or if I insist that it's connected, I will dramatically lose precision. Note that I can connect the central values because there is a translation between the two formulations. Now, in one dimension, this happens because there is a discontinuous relation between Q and Xi. But in two or more dimensions, the problem appears even if the relation is exactly, strictly continuous, because in two or more dimensions I have many more opportunities so that it can happen that the product of intervals in the Q variable cannot be expressed anymore as a product of the intervals in the Xi variables. Now, in the case of Einstein's or Forbetto's theory, explicit calculations are impossible, but the idea can be fully appreciated in a simpler system. If I consider this mushroom-shaped billiard, each trajectory can be parameterized by its initial condition, Xi equals at t equals 0. In these variables, the equations of motion are very simple. Xi of t is equal to Xi of 0. However, just a short time after t, this interval, Xi of 0 plus or minus delta, includes worlds, configurations that are very far from each other, while no matter how small is delta, while worlds explicitly, empirically indistinguishable from the central one, lie outside, maybe very far from this interval. And note that this is not a feature of this specific model. This is not the exception. This is the rule whenever we have sufficiently complex systems. It's enough to have somewhere included Newton's law that will omit these possibilities, and then I cannot use the Xi formulation anymore. So, as I said, the key issue is that we cannot express the laws of any theory as Xi equals 0 and at the same time report measurements as Xi equals central values plus or minus delta. If that were the case, Forbetto would be able to predict anything that can be deduced from Einstein theory with essentially uniform error control, uniform precision. But that's absolutely not the case for Einstein theory or for any realistic theory in which you have some quantities that can be predicted reliably with controlled errors and many others that cannot, where the errors are not under control. So it cannot be empirically equivalent to the original theory. Now, let us make this important point precise in the form of the postulate that we require for direct measurement. Whatever we mean by direct measurement, they should at least have also this property, that the result of a valid direct measurement of the property Q with precision delta is always expressed as a connected interval around the central value in this form. Q is equal to Q0 plus or minus delta, which means that the probability distribution of a single measurement has a size delta and is monotonically decreasing away from its central values Q0. To be concrete, this is a valid probability distribution of a single direct measurement. This is a valid representation of an outcome in two parameters. This is not a valid distribution, and this is not a valid outcome of a single measurement. Now, this postulate is certainly a necessary feature of any direct measurement. I cannot claim that I measured the temperature once and the result was 20 degrees plus or minus 1 centigrade or 30 degrees plus or minus 1 centigrade. This makes no sense. Cannot be the outcome of a single valid direct measurement. Now, I'm not trying to characterize what direct measurement mean. I'm simply stressing one property of valid direct measurement that I need, and I needed to exclude or penalize formulation of the Xi type. Now, once I have introduced this postulate, I can go further and can exploit it in the formulation of scientific theories in a way that I introduce as a small modification of a classic view. In fact, I define an empirical theory as composed of 4 elements: a set of principles, which contains all the assumptions of the theory from the rules of logic to the model of the experimental devices and human perception, from the background science to boundary conditions, everything I need to assume. And I assume B, a set of properties that enter in the P and are assumed to be directly measurable, in the sense that I have expressed before on the postulates. I don't need to say how they are measured. I simply assume that they are directly measurable somehow. And then also a set of results that are currently deduced from the theory and a language in which all the elements are expressed. This will not play any role in the following. I can also define measurable properties, all the non-basic measurable properties of a theory T, all those that can be reducible to observation of the basic ones through the laws of the theory R. Some remarks. The basic measurable properties are not a universal basis. There is no such a thing. All concepts are theory dependent. I'm not claiming this. I've not fixed the interpretation of the basic measurable properties. I've simply stressed that they have a specific feature of being directly measurable. No one can fix the interpretation. Correspondence rules cannot, models cannot. They simply shift the problem. The way to avoid shifting the problem is instead to put a constraint of how this measurable property, basic measurable property, should enjoy. Rather than fix the interpretation, in fact, these postulates actually exclude some implausible interpretations. Now, notice that the P assumes all what I need to check whether a result belongs to a theory, and it agrees with the experiments. For example, we can assume Maxwell equations as the principles of electromagnetism. However, this is not enough, because the principles must introduce also those properties that are associated to values and connected intervals in measurements. So I need to define also the current, charge, the electric field, the magnetic field. E and B can be assumed to be basic measurable properties within some ranges, and they are not measurable outside these ranges. There is a lot of freedom in what to choose as basic measurable properties. Actually, most of the variables which are used in science are legitimate BMPs, but not all, and certainly not those artificially constructed to trivialize the equations. Now, I need another definition, because to compare two empirical theories, which is what I want to do at the end, I want to say whether T is better than T prime. I must first recognize when two theories, T and T prime, are actually equivalent, when they are actually just different formulations of the same theory. That means I must identify the classes of equivalence. So, I will say that two theories are equivalent if they have the same logical structure and the same measurement results. More precisely, T and T prime are equivalent formulation if there is a translation between T and T prime, preserving the logical structure and the theorems, and if for each measurable property of P of T, J of P is also measurable for T prime with the same precision, and moreover, if the outcome of P is P0 for T, then the outcome of J of P is J of P0 for T prime, and vice versa. And I call this empirical equivalence. Now, going back to Forbeto theory, to really understand what is going on, consider three versions of Forbeto theory. The original one, in which I use the same variables as Einstein, but this is unambiguously more complex than Einstein. Or I may use the Xi formulation, but then this is simpler than Einstein in the hypothesis, but it is not an allowed empirical theory, because the measurements that would be necessary to preserve the prediction of the theory cannot be of the form allowed. by our postulate. Or I can have a third version in which I keep the simplicity of the assumptions. I insist that the Xi and my variables are measurable, fundamental, but then I get something that cannot be empirically equivalent to. It is a legitimate theory, but cannot be empirically equivalent to the original formulation. All this to prevent the Xi equals 0 trick. It was a long journey, but I believe this is a very important step, because once we have prevented this trick, then the rest is easy. We can basically justify Einstein's aim of science. How can we justify that Furbetto's theories and its equivalence theories are inferior to Einstein's theory? What's wrong in G of t with respect of G? Simply that now the principle P needs to connect to measurable properties. And then introducing G of t costs more words, unless I have some totally revolutionary way of connecting G of t to new measurements that Furbetto is not able to provide. And also connecting G of t to the lottery result instead of just assuming that the lottery result without much ado costs more words for just a single prediction. So it's not convenient. Can I reduce the complexity of G? Not as much as Einstein's version, unless you introduce something that is really has a deep meaning. So here would really be a theory with a different content. So once the trick is avoided, then syntactic conciseness is enough to rule out Furbetto. Let us define it precisely and define the complexity of the theory T as the minimum overall equivalent formulations of T of the length of the principles. Now, this minimum is in general not trivial, because the trivial formulation is not equivalent to original formulation, and is also as much language independent as I possibly wish, because I am taking the minimum over all possible formulations. And besides, Furbetto's theories also penalize ad hoc hypotheses. It penalizes the introduction of many exceptions. It penalizes the introduction of many terms in the fundamental laws. Now, this complexity is defined precisely, but is in general hard or even impossible to measure exactly. And this is, however, exactly what we expect from a good notion of complexity in science. Because when we compare two theories with a roughly similar amount of assumptions, we do not use simplicity to decide which is better, because we know that it might depend on unstable details of the formulation. It is often the case that we simply conclude that the complexity of the two theories is roughly equivalent, and we do not use simplicity to choose between them. Either we keep both, or we select them because of empirical accuracy. But there are also many cases where it is totally unambiguous that T is more concise than T prime. And this is especially important when T prime achieves good accuracy by easily adding many parameters, by adding ad hoc assumptions. Then here the estimate of complexity is unambiguously better for one than the other, and this is safe. And this is where simplicity is used essentially for theory selection. We often, in philosophy, overemphasize the role of simplicity in the first case, but it does not play an important role. And we often overlook this, and this is the case where the scientists don't even realize that they are using simplicity implicitly. Note also that for realistic theories, the principles might be very long, as they include assumptions from many different background disciplines, rules of logic, modeling of the experimental device, boundary conditions. It is very unlikely that we are able to gain much from a radical change of the traditional formulation. And that's why it is legitimate to use the traditional formulation to estimate the complexity. Many people are disturbed by the fact that we are counting characters in ordinary language, but counting characters might sound not fancy, but is actually natural because the scientific language evolves with science in a global optimization process. When we discuss simplicity, very often I see using these two examples: curve-fitting problem, Copernicus model. These are not good examples to understand the role of simplicity in science, because these toy models of scientific theories are not rich enough to understand the role of simplicity, because here I can actually represent them as c equals 0, and the variable c is here actually measurable. But this is very special because of the extreme simplicity of these models. It is enough to go a little bit beyond just a two-dimensional system with that admits non-trivial trajectories, and here already the C formulation that trivializes the theory is forced to use variables that are not measurable. And so the role of simplicity becomes clear only when considering theories with sufficiently complex consequences. Now, what are the consequences for Bettel's theory? For Bettel's theory, F is as empirically accurate as the theory E, which is Einstein's theory plus the assumption of the lottery outcome. Just plain assumption of that 6 numbers. Now, F is unambiguously less concise than E, because G of t is certainly less concise than G. And assuming the lottery outcome without much ado is certainly more concise than trying to connect to GDT somehow, since anyway some more assumptions are also needed. Now, F has the same accuracy and lower conciseness than E, so E is better. This is what we define as better than F. So let me summarize. We have a postulate of a property which is necessary of direct measurement. We have a definition of empirical theories that includes the principles, and in these principles we must label somehow some concepts, some properties as directly measurable. We can define also the other measurable property constructed on top of the basic one. We need a notion of equivalence, which is just logical equivalence and empirical equivalence, and a notion of complexity. And finally, we have defined better theory T better than T prime if it is better in terms of either accuracy or conciseness without losing on any of them. Now, this enables us to define the state of the art as those theory for which there isn't any other theory that's better than them. And the demarcation, because scientific are those disciplines that rely on the state-of-the-art theories, while those disciplines that do not rely on state-of-the-art theories are not scientific. Progress equivalent can be stated is characterized by the fact that state-of-the-art evolves, because previously theories that were previously at the state-of-the-art become superseded by new theories which are better. So, going back to Einstein's original statement, the grand aim of all science is to cover the greatest number of empirical facts by logical deduction from the smallest number of hypotheses. This is almost right. We can do it the conclusion of this talk is that we can do it a bit more precisely by reformulating in this way that the grand aim of all science is to cover the greatest amount of empirical data by logical deduction from the smallest amount of assumptions, measured as the length of the most concise formulation available that includes enough directly measurable properties to derive all properties necessary to describe the empirical data. Now, let me discuss just two examples to address the following questions. Sometimes new theories take some time to be recognized. They are only gradually recognized. How is this compatible with a model in which I clearly defined when a theory is better than another? The second question is, how does my model rule out non-scientific theories, realistic non-scientific theories, not just furbetto? So let's review one by one. For the first question, let's consider the evolution of how Einstein gravity has been introduced and accepted as a better version than Newton gravity. In 1915, Einstein gravity was introduced, which explained the precession of Mercury, which was a problem for Newton gravity. So already back then it became more accurate than Newton gravity. Why wasn't it accepted immediately? Because, first of all, people could think of other possible consequences of Einstein gravity that were not clear, because people could not derive immediately all the possible consequences of Einstein gravity. And moreover, the complexity of the assumption of Einstein gravity was also not clear. On the other hand, Newton gravity had only very few anomalies, only one, the precession of Mercury. And that could be saved with a few lines, with a few ad hoc assumptions. Now, in 1919, the bending of light was observed, and this became another factor, another advantage of Einstein gravity with respect to Newton gravity, even with the ad hoc assumption needed to take care of the precession of Mercury. Then one could introduce a new version with yet more ad hoc assumptions. And then the more evidence is accumulated, the more ad hoc assumptions are needed to save Newton gravities. And at some point, the ad hoc assumptions are too many that they cannot even be written on a page, and the conversion then to a new paradigm is based on well-defined properties, although their assessment is difficult, takes time, and includes some uncertainty. But at a certain point becomes more and more unambiguous. Complexity, conciseness is evaluated, is assessed, and has error bars, just like any measurement in science. Let me give you here an example of non-scientific theory. Intelligent design has been criticized by many authors, see for instance Sober and references there. However, these criticisms do not address a subtler version of intelligent design that I call here ID star. And this ID star is formulated as following. ID star accepts all standard theories, including evolution, except that occasionally and precisely in front of complex biological structure for whom the current evolutionary explanation seems to have puzzling, low probabilities, then ID stars postulates the intervention of a designer, also nicely called God of the gaps. Now, such gaps are indeed problems for the standard theory, and they need some ad hoc assumptions to fit. Now, ID star is empirically accurate, is predictive, falsifiable, testable, exactly as the standard theory. All okay, as much as the standard theory. The key point: can I postulate The key point is the following. Am I able to postulate a designer that probably improves the likelihood of those evolutionary events and is more concise than just postulating that those evolutionary events occurred somehow? No, such proposal does not exist. The designer has no deductive value. Therefore, it is superfluous and hence non-scientific. So the fundamental problem with the intelligent designer, which now includes also ID star, is that ID star does not even attempt to do what science must do, deducing as many phenomena as possible from as few assumptions as possible. Instead, ID star de facto simply claims that the goal of science is sometimes not attainable. Skepticism about scientific progress is legitimate, but it is not itself scientific progress. Now, I've claimed that the progress in science can be explained in terms of empirical accuracy and conciseness. Do we need other values beyond these? It is often claimed that there are many variables to be taken into account. Don't know how many. I do not see this need. For example, logical coherence. We choose the rules and we stick to them. This is not negotiable. Logical coherence is a precondition, not a value in which we can trade. Aesthetic coherence, often related to elegance, symmetry. I'm not aware of any case in which a scientist has appealed to such values that could not be translated into more conciseness in some formulation. If you have examples, please challenge me. Fruitfulness. If an idea is fruitful but has not materialized its fruits yet, let us wait. It is not a value yet. Explanatory power. What is it? Explanatory power besides higher accuracy with fewer assumptions. Number of parameters. This is a particular case of conciseness for very similar theories. Likelihood of the assumptions. It is impossible to ensure this for all assumptions. We will always need assumptions which we cannot evaluate this likelihood, because the likelihood we can deduce it from some other assumptions. Better fundamental justification. Well, this is also a case in which, by appealing to better fundamental justification, we are actually reducing the number of assumptions overall. So I really do not see any need of independent cognitive values beyond those that I've already included. Finally, science relies on non-empirical cognitive values that are essential to justify its conclusion. We need to identify them clearly. And this is not impossible if we understand the interplay between simplicity and measurability. Simplicity alone is not enough. Measurability is the key. Are conciseness and empirical accuracy enough to define the goals of science? I see no exception to this rule. In particular, I see no exception to the rule that the grand aim of all science is to cover the greatest amount of empirical data by the logical deduction from the smallest amount of assumptions measured as the length of the most concise formulation available. That includes enough directly measurable properties to derive all properties necessary to describe the empirical data. Please show me counterexamples. Thank you.